Okay, for this lecture, we're going to provide a little shortcut. It is known as the Henderson-Hasselbalch equation, and we're going to derive it really quick. What we are familiar with up to this point is when you look at the expression for an equilibrium for an acid, you've got the whole products over reactants. And I'm seeing how, that's fine, I'll leave it as X. I'm feeling a little uncomfortable with that, doing it, because normally I do A, but my notes are putting this at, and I'm just gonna go with it. Okay, if I rearrange this equation in terms of H, hydrogen ion, I wanna focus on that. So I'm just gonna separate that out from the mix, and then just bring everything else over to the other side. I end up with Ka, and I could put it together, but I'm going to show it like this. Hx over x minus. Okay. Now if I take the log of both sides, what I will get, negative log, excuse me, I will get negative log of H plus, that should be familiar, is equal to the negative log of this whole mess, put brackets around it, and of course I can kind of separate these guys here, and I'll just leave this alone over there just for the moment and get negative log of Ka plus, or excuse me, minus the log of Hx over x minus. And I can go one more step here. I'm going to turn this into something else a little more familiar instead of negative log of the concentration of hydrogen ion, and just call it pH. And I'm going to do the same thing to this factor here. We can do that. pKa. And also in doing this, I'm going to kind of flip these around a little bit and say positive. You'll see what's going on here in a second. And flip these guys. We can do that. By changing the sign, we flip the two factors. Okay, and so this is pretty much the Henderson-Hasselbalch equation. As long as we know the Ka value, and we know the acid and base concentrations at equilibrium, we can bypass that whole process we were doing earlier and just go with the answer. And just to kind of clarify how this is looking here, in case you don't see it as clearly, all we need in this little equation here is the concentration of the base over the concentration of the acids that are given at equilibrium. So let's go ahead and do a problem, and we'll see how this plays out. We're on 21. So for 21, it says calculate the pH of a buffer that is this concentration of the acid and this concentration of the base. We'll show it both ways just so we can see and show that it works. So normally, up to this point, we would make ourselves a little rice table. We have acid dissociating and giving us this. We put in the concentrations that we have for these two guys. This for this, for this, and for the base. It's going to dissociate some. We go ahead and put that value over here. It's about the same. And then we take a look in the back of the book for the Ka value. The Ka value happens to be 1.4 times 10 to the negative 4. Put in the concentrations that we have. solve for x. X is 1.53 times 10 to the -4. That is equal to the hydrogen ion concentration. Do negative log of that value, and you get 3.82. Very good. Fantastic. Now let's try it using the Henderson-Hasselbalch equation. We want to solve for the pH. We will take the negative log of the pKa value. So I will say negative log of the pKa, or Ka value, plus the log of the base over the acid. There's the base. And that was initially given to me. But of course, it is that value at equilibrium if I assume that everything that is gathered or lost is about negligible. Okay, so if I just run this through my calculator, I will get an answer of 3.82. Yeah, that's true. Done. Now let's do this one down here. And we'll have to, well, we don't have to actually. We can just run this through based on the information that we're given. Calculate the pH of a buffer that is formed by mixing this volume and this volume of these guys. We do have to do one little step here to make it true. We have to get the new concentrations for these. So we will kind of set that up based upon what we did in an earlier problem, in which I have a concentration which is 0.13. And we will multiply times its volume, which is 85, and then divide by the new volume, which is going to be 180, 85 plus 95, and that'll give us a new concentration for the acid, which is 0.0614, I believe, molarity. And I'll just go ahead and write that down, HA. If I do the same process for the base, that'll be 0.15 times the 95 mils divided by the total same volume of 180, and that'll give me 0.0792 molarity of the conjugate base. Okay, so I have those two values ready to go. Let's go ahead and just plug it into the equation. So pH is equal to negative log of the Ka value, and I'll take a look for acetic acid. We've done this a few times again already. 1.8, or excuse me, 1.4. What's lactic acid? Excuse me, I said acetic acid. Lactic acid. I was like, hold on a second, that number is not familiar. 1.4 times 10 to the -4. Plus the log of the base over the acid. So therefore it is 0.0792 over 0.0614. Run that through and you get 3.96. Done. Okay. Let's take a look at, I think we're going to be done with this one, and we'll go back over to our notes. Oh, there's one more thing I wanted to show in doing this kind of a problems. So we got that one done with the Henderson-Hasselbalch. I just want to show kind of what this will mean for us. And we haven't done a lot of work with this yet, but I'm just going to mention it right now. This equation here being the process of putting those values in, what this is really good as far as working with a buffer. Buffers are things that resist changes in pH. And you do that by having two things that work really well. They don't have much effect on the pH themselves. A weak acid doesn't dissociate well. Its conjugate base also doesn't accept hydrogens very well. So, which is when you're dealing with a buffer, you typically want a match of a weak acid and a conjugate base. So when we set this up, and you look at a titration, as we maybe have looked at before, but we're definitely going to do some of that in this chapter. You're adding some base. Usually it's strong. And of course, you can do this from the other direction as well. I can spell strong. It can be the other way around, but in this case, we're starting off with a weak acid, and we're adding volume of a strong base. So as we add it in, we're starting off with only acid present, and the pH is very, very low. Like I say, like 2 or 3. And then as you're adding the acid, or excuse me, the base, as you're adding the base, the pH, of course, is going to go up, and we're going to see it reflected. The pH will go higher and higher until all of the acid is gone. So at a point in which you have added equal volume, or I should say equal number of moles, to the acid that is present, then you get what's called the equivalence point. At the equivalence point, I have equal moles. So I'm going to write that down. At the equivalence point, we have equal moles of HA and OH. So therefore, they've neutralized. So you just have water and salt. So the pH is relatively like neutral. You may say, oh, well, therefore it's going to be 7. Not exactly. We can talk more about that later. We're not going to do it exactly at this point. But at this point, we're going to assume that we have gone through the equivalence point, and we have this, I'll just call it a point at this location. All right, let me pause here, and we can get into a deeper, fuller, finishing explanation in the next lecture. Okay?